Well, we're going to be looking for an equilibrium constant Kc, but we know that that's the same thing as the thermodynamic equilibrium constant K, and we have a relationship between the thermodynamic constant and Gibbs free energy. So we're given some Gibbs free energies of formation. So if we could figure out the change in Gibbs free energy for the reaction, then we can plug into this and get our thermodynamic K, which is Kc. So we're going to start by getting our Gibbs free energy for the reaction. And this is where you do products minus reactants. For this N, that's where we use the coefficients. So I'm using this coefficient 1 with this number. This 1 with that 0. Just showing all the numbers that I'm using. Okay, and we did all that. Let's look at the math. These numbers were in kilojoules per mole. And so in a way, the moles cancel with these coefficients. I'm going to go ahead and put kilojoules here. But keep in mind that when we do a Gibbs free energy for a reaction, just like at the enthalpy for the reaction, it is implied that that's kilojoule per mole of the reaction, and that will come in handy. We'll need that unit here in a second. So that's in kilojoules. Okay, that's the first part, and now we're going to use that equation that I wrote above. And we need to watch that this K, it's a big capital K. It's thermodynamic K. It's not Kelvin. It's not a kilo or something like that. And then notice that this R, the R here, it is the same constant as the universal gas constant, except it's in different units, which is kind of strange, but really it is just a factor that comes into play when you have particles in random motion. So it's a different number because the units are different. But notice that constant, this constant has joules, and we're going to need it to cancel with this. So we need to get our delta G into joules so that it'll cancel in this reaction. And so I can do that pretty easily just by doing this. So put in a 10 to the 3 to take the place of the K there. The temperature, all of this, and I didn't write it right here, but we were dealing with standard temperature, thermodynamic temperature. So that's 25 degrees C. Let me just put that. Okay, and so that's where I get the 298. Let's look at how things cancel. I have this joule will cancel with that one. I'm just dividing both sides by joules. Be careful with these K's. This is the temperature K and this is a temperature K, so those cancel. And then for this moles, remember that we kind of said it's really kind of joules per mole of reaction. So that's how that one is canceling. So all the units cancel. Let's clean it up. And we need to solve for our thermodynamic K here, and to do that I need to take the inverse log of both sides. And just to remind you, the inverse log of x is the same thing as e to the x. Okay, so it comes out to a huge number. Let's look at sig figs real quickly. Technically, oh, I didn't show that step. Let's just put it in here. This was so this is the number that I actually took the inverse log of once I put all that in. It really only has 3 sig figs. And so, but remember, when we're taking the inverse log, we only look at the digits past the decimal. So this is kind of like it has 0 sig figs. Anyway, you're basically that means that you're getting a magnitude. And so since this is over 5, I would say this is like I have 10 to the 53. But anyway, you know that it's a really huge number. Does that make sense? Well, saying that this is a really huge number means that the products are really favored because equilibrium constants are products over reactants. And if we go back here, we see that our Gibbs free energy was negative. That would mean that it's spontaneous. The products are favored. So that makes sense.